So in this experiment we are going to determine the Stefan Boltzman constant for the given material. So radiation heat transfer is the mode of heat transfer in which heat transfer takes place without any medium. So it takes place in the vacuum form. For example, energy of the sun reaches earth by radiation. Heat transfer takes place in the form of electromagnetic waves. A black body is the one which absorbs all the radiation. Stefan Boltzmann law defines that radiation energy emitted by the body. The law states that the radiation energy emitted per unit area is directly proportional to 4th power of absolute temperature of the surface. The proportionality constant is called the Stefan Boltzmann constant, which is usually represented by sigma. The value of the sigma is 5.67 into 10 to the power of minus 8 watts per meter square Kelvin to the power of 4. So now let us discuss the apparatus setup. The setup consists of hemispherical enclosure made up of copper connected to the flat plate. So this, what you can see, this is a hemispherical enclosure made up of copper inside and connected to the flat plate. This enclosure is enclosed by water jacket to supply heat by using a hot water. Inside this we have been having what we say the water jacket, so through which the heat is being supplied. For that, the hot water is being passed into that water jacket. The hot water we are being going to get from this heater. Here the thermocouples are provided at the outer surface at the copper enclosure, so that we can't see here in this. They have been placed inside. A small copper disc is provided to absorb the heat radiated from the enclosure. This disc has to be inserted in the hole provided in the center of the top face of the plate. The electric heater is provided to supply the hot water continuously to maintain a constant temperature in the enclosure. So this is where you can have a pipe where the water is being transferred continuously. So here let us find out the specification of disc what we have been having. The diameter of the test disc that is being taken as 20 mm, and mass of the disc is 10 grams, and density of the disc is 8.93 kg per meter cube, and specific heat of the disc is 385 joules per kg per Kelvin. Now let us find out how the procedure is being carried out for conducting this experiment. So fill the water in the upper tank, then switch on the water heater. So we need to fill the water here in this tank. So switch on the water heater and allow the water into the enclosure. So for this one heater we are going to on. Okay. So here once the water is been made fill up, then you are going to on the heater. So we are going to wait for a few minutes till the enclosure temperature reaches in a steady state. Now note on the enclosure temperature and insert the copper disc in the hole provided in the plate. So here you can see that pipe is being connected. Note down the disc temperature at every 10 seconds time interval and repeat the experiment for different enclosure temperature. Then afterwards you can calculate Stefan Boltzmann coefficient using the formula. So here we will see the experimental tabulation, where you can find out the temperature of T1, T2, T3, T4, T5, T6 from the thermocouple. And here we have been finding out the time in seconds for which the temperature T7 for different time intervals we are going to find out, from 0 to 30 seconds, then 60 seconds and 90 seconds and 120 seconds. Okay, so here we have been having a Stefan Boltzmann constant equation, where m is the mass flow rate and Cp is a specific heat, and the dt by dt, that means we are going to draw a graph for the disk temperature with respect to time. From that slope we are going to get dt by dt. Then the area of the disk we know, then the temperature to the power of 4 of T5, and with respect to the temperature of T7 that is been calculated at different timings, we are going to substitute over there. So here the area of the area is the surface area of the disk, that is pi d square by 4, that the value of small d is been given standard, and for the surface temperature we have been taking T2, T3, T4, T5 and T6 average of that one, and we are going to add 273 Kelvin. Next temperature for T7 also we are going to identify. So substituting those values in this equation, we are going to get a difference, and the area also we are going to get it, and mass flow rate we know, and the value of Cp also we know, that is in a specific heat of the copper. Then from the graph we are going to find out dt with respect to dt. Okay, so substituting these values we are going to get a Stefan Boltzman constant.